Hello, and thanks for the invitation to speak here at this symposium. I have to apologize, I cannot be here in the live session. It's a time shift actually that made things rather difficult for me to join directly. No matter what, I'm really happy to be here and talk about on-skin computing in my presentation today. So 10 years of augmented human research is a long time. And as a matter of fact, Suranga and I have met pretty much exactly 10 years ago when both of us were visiting faculty in Paddy Mace's lab. And here's a few photos I found about that time. And on the left-hand side, actually, we see some demos and prototypes of iRing, work that Suranga has been conducting back then at the MIT Media Lab. And funny coincidence, there is also some photos and prototypes of Cloud Drops, a project that Suranga and I have worked on together on small displays that are dispersed in the environment. So congratulations on 10 years of research and my best wishes for a next decade of joyful and fruitful research on augmented humans, Suranga. So I'm particularly interested in how we can use skin to enhance perceptual capabilities of our human body. Skin is our largest organ to perceive the environment. And as a matter of fact, it's the sense that is the first to develop when the fetus grows in the uterus. Also, our skin is multimodal. It comprises diverse types of mechanoreceptors that can capture a wide range of stimuli. And I've always been fascinated about the rich ways of how we use our body and in fact skin to interact with the environment. Just think of these rich ways of how we perceive the materiality of surfaces and objects and how we act on objects and how we manipulate and deform them using our body and using our own skin. But skin is also a means for self-expression and tells us a lot about ourselves. For instance, skin is a strong and great site for capturing biosignals. So for these many reasons, actually, we've been interested in investigating what we call interactive skin in a multi-year-long ERC project. And what we propose here is a new class of wearable devices that are micron thin and made of stretchable materials that create novel types of interfaces that are highly ergonomic to wear on very diverse sites on the body, including the highly deforming and complex geometries of the skin. These make use of the large surface that skin is offering us and can support high resolution and multimodal input and output. Amongst others, we've been working intensely on tactile sensors, on visual displays, on haptics, and also now increasingly on physiological sensing. And actually, these are two topics that I would like to talk about today. One is how we can enhance our human tactile sense using these new devices. And secondly, how we can leverage physiological sensing as a means of input for enhancing human senses. And of course, a lot of work has been done on augmenting human senses, mostly in the visual domain, maybe also in the auditory domain, but comparably less work has been in the tactile domain, where we are still sort of in the early days, in the infancy of research. And let me explain our rationale behind the work that we do here. So if, once again, we look at the visual domain, we have interfaces that allow us to see through. This is classical augmented reality, where essentially we have, for instance, augmented reality glasses that allow us to see real-world visual cues and superimpose those cues with computer-generated visuals. And this now creates this blended environment where we have both the real world and computer augmentations in the visual sense. How about the auditory domain? Probably less frequent, less common, but still there is technology that allows us to do something similar, devices that we can hear through. Think, for instance, of bone-conducting headphones. These keep our natural hearing intact, allow us to attend to real-world auditory cues, while at the same time they can superimpose these, augment these with computer-generated audio cues, like, for instance, a live translation. But how about the haptic domain? How about a feel-through interface? An interface that lets us feel the profile of this tire and at the same time overlay tactile information. Of course, this would not work with this actuator. Here, this is easy to see simply because the hardware in the haptics domain tends to be too rigid and too bulky to transmit tactile cues from real-world surfaces or objects we've been touching across these interfaces. And in order to address this problem, we actually have worked on very slim membranes that allow us to feel real-world cues and at the same time augment these with computer-generated tactile stimuli. And as a matter of fact, this is work that we have done together with Anusha, who used to be a PhD student in Suranga's lab and then did a postdoc in my lab. And here we see on the left-hand side, Anusha wearing one of these devices on his fingertips. Here's a close-up of the device on the left-hand side. So you see it's a slim membrane that is worn on the finger pad, or also on other areas on the body. It's very thin, measures around 35 microns. So it is thinner actually than the diameter of a human hair. And this allows it to be conformal even to tiny wrinkles of the human skin, as we can see in this close-up photo here. It features a high textile density of textiles that can be separately addressed, also at a high frame rate. And we use printing for this purpose, so it's easily customizable to work on different body locations. So here on the right, we see an example that is deployed on the user's forearm. Now, a problem is, of course, to integrate tactile output inside this very demanding, very slim form factor. And in order to make this viable, we opted for a known technology, which is electrotactile stimulation. It makes use of small electrodes that are directly contacting skin. And then with a small amount of current that is offered through these skin-exposed electrodes, one would excite nerve endings of mechanoreceptors, and those then in turn create a sensation which is quite similar to mechanical vibration. But the key benefit is we do not need a mechanical actuator, so we can integrate all of that in a slim package. But the problem is that in order for this to work, those electrodes demand for very strong and consistent skin contact. This is not an issue if we have a classical, say, benchtop or tabletop setup where one is touching a rigid surface. But in our case, with those very slim membranes that we have, this is demanding to realize. And so what we did here on the fabrication, on the technical end, is we devised a new layer design that makes use of new materials in such a way that these individual electrodes that we can see here have a very strong contact to the skin. Actually, we do this by printing them with slightly thicker materials, and that this creates a mechanism that we call microsprings, where this flexible membrane here itself ensures that all of these electrodes are tightly in contact with the human body. So why is this important, and what would it allow for? It allows us to devise new types of interfaces for tactile augmented reality. So where really the idea is to enhance our natural tactile sense. So for instance, the feel-through properties of the device enable us to support a designer working on a model car to feel, first of all, of course, the rubbery texture of this real tire that we see here. But then at the same time, our device can, for instance, create virtual tactile features such as engine vibrations that might be simulated. And it can then be felt on various locations of the object. This is visualized here. And given we have full control of the intensity, we can also very essential various aspects here. We can augment our body with tactile information. For instance, to create dynamic landmarks for on-body interfaces. So in this case, we augment the tactile perception of touching one's skin and leveraging those many tactile landmarks that the body is offering. And we can augment those with computer-generated cues. For instance, virtual buttons could be rendered, and even the active or passive state of those buttons could be rendered with this device. Another example is virtual reality, where typically one can see virtual contents, but one cannot feel them. In our case, Tacto can be used to create rich tactile sensations in virtual reality. For instance, one can feel individual needles in this example here, or one can feel larger elements such as branches or the stem. And given we have full control of individual textiles, we can actually render the differences between small, tiny features and sort of larger surface features. And here's an example of how the device can be used. We visualize the stimulation on the left-hand side. So for instance, this allows for various types of notifications on real-world objects, for augmenting one's body, or as I just mentioned, for creating haptic experiences in virtual reality. Now, a central question for validation this overall principle is, of course, to find out if this device actually really has feel-through properties. How well does it allow us to feel real-world cues across this membrane? In order to investigate this, we did a first pilot evaluation where we worked with a tactile chart. You can see on the left-hand side, where basically people had to feel those surface features and correctly identify the direction of those features. And then this allowed us to identify tactile acuity. This is plotted here. In this case, lower means better. So what we see is that bare skin, unsurprisingly, has highest tactile acuity. And then the interesting observation is that our Tacto device comes really close to bare skin here with only minimally decreased tactile acuity. On the right-hand side, we have a baseline comparison. This is a device from the state of the art that is made of silver. It's also very thin, a tenth of a millimeter, but slightly thicker and slightly more rigid than ours. And we can see that this has actually a significant effect and significantly reduces the tactile acuity compared to both our device and Bearskin. After this pilot, we were interested in investigating those tactile aspects in more detail to really understand how we can use such devices to enhance natural human tactile perception. And we conducted extensive psychophysical experiments and follow-up work that was published later at CHI. Here we investigated 3 areas: tactile sensitivity, spatial acuity, and roughness discrimination, and wanted to investigate to what extent membranes of different thickness or rigidity would decrease those perceptual capabilities. And here is just one aspect of our findings. If you're interested, please have a look at the paper. All details are in there. What I would like to highlight here is the following. So what we see in this chart is in red, the Bearskin condition, and actually lower here means better, higher sensitivity. And what we see is in green that the low rigidity device, this is corresponding to these tattoo devices that we've seen before. This device comes very close to the sensation of Bearskin. If you have slightly thicker device, these still perform surprisingly well, but then we can see a stronger difference. These devices here actually are made of PDMS, a medical grade silicone, which is slightly thicker than the tattoo devices that we have here. So a second aspect I want to briefly touch upon is physiological sensing as a means for supporting perceptual augmentation. So classically, if we wanted to do physiological sensing, one would capture signals with so-called wet electrodes. These are fairly thick electrodes, as you can see here. Fine for medical context, also fine for prototypical proof of concepts, but of course, this would not scale to a real wearable or long-term use. So what we proposed in our work is a way to realize ultra-slim electrode tattoos for sensing EMG, ECG, electrocardiogram, and EDA, electrodermal activity. And so what we do here is actually we print conductive traces, insulation on multiple substrates. And as a matter of fact, all of this is compatible with use in do-it-yourself kits for reading those EEG, EMG, or EDA signals. We've explored diverse materials and investigated not only temporary tattoos, but also TPU and a slightly thicker elastomer, textile transfer paper, and PDMS, which is a medical grade silicone. A key question of this work was not only fabricating those electrodes, but then of course also investigating how close do they come to this baseline setup here where we have these more cumbersome electrodes. So we conducted an experiment with humans. I will spare you the details. The only point I want to highlight here is that the signals that we can pick up with these printed electrodes come surprisingly close to the quality of those commercial electrodes. Here below you see the SNR plotted, the Pearson correlation, and you see that particularly the tattoo paper comes really close to commercial electrodes. This here is for EMG, this is for EDA, and here for ECG we see a similar behavior. Let me just show you 2 examples of what can be done with this. One example is a fitness tracking sportswear. Here the idea is that we actually print the electrodes on temporary, well, it's not temporary, it's actually a textile transfer film. So we print on this film and then using an iron, we would transfer it onto textiles. And so this gives us a sportswear that we can see here that captures signals in 2 EMG channels here, so muscle movement from 2 muscles and also heartbeat using electrocardiogram. And all this can be fabricated really fast in 15 to 20 minutes. And then we have a very slim, very wearable form factor that we can see here. And then this allows us to pick up these signals. For instance, in this case, the muscle movement, the EMG signal that you can see here. So this comes in quite handy for all types of fitness-based or physiological applications. Another example is an interactive heart rate tattoo where we sort of sense heartbeat and heart rate with a device that is fully printed. And here you see the device in action. It's a very thin tattoo that we can see here. It contains the electrodes and allows the user also to interact with it using touch input. And then we can use this for various types of interactive applications where heart rate needs to be detected. So in conclusion, we have seen that micro and thin interactive devices can be realized that blend with human skin and are very ergonomic to wear on diverse, challenging body locations. Various types of multimodal sensing and visual and haptic output can be integrated to offer various forms of how we can support human perception, augment human perception. But of course, it has to be noted that what I presented today is just the very beginning, essentially. With Tacto, we could show how we can superimpose and augment tactile perception. But for instance, we have not shown if and how we can modify and alter the perception of real-world surfaces. So particularly this perception feedback loop needs to be investigated in much more detail. And it's also that, of course, this skin platform offers opportunities and various opportunities of how we can support perceptual augmentation using diverse body locations, using diverse modalities, and all of them, of course, demand for much more investigation in future work. Thank you very much for your attention. And again, I'm sorry I could not join the live session, but I'm happy to answer any questions that you might have or engage in some discussion. Please just drop me a note and we can find some time to set up a Zoom call or similar to engage in a bit more depth with each other. Thank you. Bye-bye.